Alright, so today we're going to look at the temperature dependence on the rate constant, K. Uh, as we discussed in earlier videos, the differential rate law is given by this thing here. Now, however, we also told you that, we also know, however, that reaction rates are not only dependent on reaction concentration, but also on temperature, and it's the rate constant, K, that is temperature dependent. Rate constants and consequently reaction rates increase as temperature increases, just as we described using the collision model, because molecules are moving faster and therefore can have more collisions per unit time, and since they have more kinetic energy, they have more particles meet or exceed the activation energy required for a reaction to occur. We can use the Arrhenius equation shown below to quantitatively represent sort of K and its temperature dependence. K is the rate constant, A is just a frequency factor constant, activation energy is the activation energy, R is the gas constant, and T is the temperature in Kelvin. The frequency factor A is a pre-exponential factor which relates to the orientation of molecules, the number of successful collisions, and all that stuff. It's just a constant, really. And the graph is just a plot of the equation with K versus T, and as you can see here, it grows exponentially, I should say. It's exponential, K versus, temperature. It looks sort of like this, which is sort of exponential, but sort of not. Yeah, here's sort of a sample equation. It's just a formula. I'm not going to go over how this works. I'm sure by now you know how to plug and chug numbers into a formula. However, the only real interesting thing here is that we can use some techniques to what we call linearize this graph, and linearizing the graph essentially makes it in the form of y equals mx plus b, and the way we do that is since we have this exponent here, we take the natural log of both sides, and by the properties of exponents, we can split this product up into a sum, and since this is ln e to some power, the power comes down, again by the rules of exponents, and then we know that ln e is just 1, and we get ln k equals ln a times activation energy over r times 1 over t, and we can rewrite it in this form. And so if we were to graph this, the slope would be minus EA over R, and the y-intercept would be ln A. Now, I think what's important to note, you don't necessarily have to remember this. If you're good with math and exponents, you only really have to remember this step here, and if it asks you about the linearized form, you can quickly linearize this, assuming you're good at math. If not, that's sort of the process of how you would go about linearizing it. And then we can use this to derive some other equations, which is ln 2 over ln k2 over minus ln k1 is equal to this ugly expression here. No, it's equal to this expression here, which we can derive from, here's the derivation of it. Here's the second form of the Arrhenius equation, and then there was a third form, which really doesn't matter. There was another form of which I'm sure they're all given in your formula booklet, and this is really just as easy as plugging and chugging numbers into the correct formula, and there's really not much point in going over it. So that's about it. So yeah, thank you for watching.